Alright, this is our first official video. It's about Chapter 1 and the linear stuff in our textbook. After watching this video, so I guess the order that I'm imagining this happening is you can watch this video first to get my idea of what's going on. Then you should go on to Blackboard and you should look at the in-text examples. And lastly, log on to WebAssign and try to solve those problems. It's not necessary to do this each and every time. Obviously, if you're good at something, and particularly it's possible here in Chapter 1 that you're probably already good at this stuff. This is the start of probably Algebra 2, College Algebra, a lot of classes. But this is what I'd call my formula for success. If you do these things, watch the video first, then use that to work through the examples. And when I say work through an example, if I say, look at example 2 in section 1.1, then you're going to want to look at that example, you're going to want to work your way through it. If there's steps that it's skipped, you want to work those out with a pencil and paper beside you. I have this idea called active reading. And it's how a math textbook should be looked at. You always need to have pencil and paper, pen and paper, something that you can write on, doodle with, as you try to read through an example and understand what's going on. The biggest thing that I ever hear that students say that makes me cry deep down inside is that they say, okay, I didn't understand the examples, so I skipped to the homework. There's some variation of that. And that, of course, is completely crazy, and I don't understand it, because if you can't work through an example in the book where the textbook's giving you some of the information, generally going straight to the homework doesn't help. And I know some people mean different things when they say that, but generally that's my feel. It's the example does have some of the pieces. It might not have all the pieces, and so it might be difficult to understand. But the textbook examples I select do have some value, so I really do encourage you, look at those examples, watch the video first, then tackle the WebAssign homework. If you do that, you will have already, by the time you do the homework, you'll have practiced a particular concept. You'll have seen it 3 times, which means you're well on your way to reviewing for the exams. Something to keep in mind, exams are closed book and closed notes. The one exam from one of the sections in dealing with financial formulas, you'll have a little sheet of financial formulas. That's the only time you don't have to have something in your memory. So if you follow this process carefully and work through this stuff, the homework will go a lot quicker as a result of doing these 2 things. And also, it'll just build in the review, and then you don't have to review for an exam specifically. I've been a student before. I know everyone says, read the book, then go to class, then read the book again, then work through the examples again, and then do the homework, and no one ever does that. But if you're having trouble, you take that first exam and you don't like your grade on it, consider trying this. Alright. So, end of my soapbox. Let's talk about linear processes that are going on. Linear process just means a straight line. And I think everyone in this country, we usually have x, y, there's negative x over here and negative y over here. I don't know, I have points 1, 2, 3, 1, 2, 3, negative 2, negative 4. So I can have some different coordinate points. This point right here would be negative 4, 3. We always do x, y. Again, that's in this country. If you don't write any of these labels, so if you didn't have the negative x, the negative y, positive x and y, I would assume that this was x and this was y. You come from a different country, or you learn from a different country type of textbooks first, you're free to do that. I can translate. You're just going to want to let me know what's going on here, and of course watch out, WebAssign isn't all that clever, so watch out that WebAssign is expecting this to be positive x and this to be positive y. I know of at least 2 other countries that do things in a different fashion than this. I can translate if you're just talking to me, but WebAssign I don't think is quite as skilled at translation. So that's the coordinate point system, and then if I have this other point over here, let's say the point 2, 1, I might eventually decide that I wanted to connect these 2 dots with a line. This would be a linear line. It's a straight line. That's what linear means. For this linear stuff, we've got some ideas. Our very first idea that we have is the distance between these 2 points. And some of the homework sections, particularly some of the word problems talking about boats and stuff, start with this distance formula. So here is the distance formula. Let me write it out here. D is equal to the square root. This is my D, lowercase d. That's just how I write it. D is equal to the square root of x2 minus x1 squared. Oh my, double square roots there. I'm a little excited. X2 minus x1 squared plus y2 minus y1 squared. Doing the stuff inside the parentheses first. All of these things under the square root. Let's talk about why this formula makes sense. You could just memorize the formula. That's possible. Don't get me wrong. I'm a big fan of memorizing and not understanding. But in a class like this, I generally feel like there's too much to memorize. So I try to build into my mental thought process a story. Why is something true? Why should this be my instinct? A good idea. If you get something wrong a lot, you solve a problem, there's that one problem that you always get wrong, really tackle that problem, look into it, find out why you get it wrong. Usually if there's something that you always get wrong, and you hear people say, oh, I always mess up that one. There's a reason. That reason is usually there's something broken. This sounds cruel, but it's actually not. Broken thoughts. If you get something wrong all the time, there's a reason. There's something in the way the real world works that you're understanding wrong. You can go onto Wikipedia. It's kind of cool. There's a place called Common Misconceptions. And it lists all the stuff that we believe is true as a general rule that is not actually true. For the longest time, I believed that glass was something called a supercooled liquid. And that's why if you go into old buildings, the thick part of the glass window is at the bottom. Well, we have a word for supercooled liquid. It's called a solid. And it's just like every other solid on the planet. And the reason the thick part of the windows is there in old buildings is because when you put in a window and it has a thicker part and a thinner part on the glass, you put the thick part down so it doesn't snap off. So go back and find what your broken thoughts are if you keep on getting a certain type of problem wrongs and fix those thoughts. Start understanding the way the world actually works instead of the way that you thought it worked wrongly. Alright, so here's the distance formula. Again, you could memorize it, but it actually makes sense because it's secretly the triangle formula. Everyone has seen c squared equals a squared plus b squared. It's called the Pythagorean Theorem. I had a professor once who told me that the three things that made us better than monkeys was the Pythagorean Theorem, nuclear weapons, because I guess that baboons don't have nuclear weapons, and also he was a very large fan of pizza. So those three things were why we were better than random mammals. Anywho, here's my 2 points. This is my point, x1, y1. And here's my point, x2, y2. It's a little sub 1, sub 2 going on here. And I'm trying to find the distance between these 2 points. But of course, there's something else going on here. If I do this, that completes the triangle. This right here is height y1. This right here is height y2. This right here is point x1. This right here is point x2. If I do my general Pythagorean formula, it says this: c squared, which is this part right here, equals a squared plus b squared. Here's distance A, and here is distance B. But what is c squared? Well, it's the a squared part, but what is the a squared? It's the x part. So it's x2 minus x1 squared. x2 minus x1 gives me this distance. Plus, and what is b? It's the y differences. It's the y2 minus y1. That's my y height. We might normally think of positives, so I would say, well, it's this y1 height minus this y2 part. But remember, I'm putting it inside parentheses and squaring it, so that will get rid of the fact that if I did y2 minus y1 in this case, that would give me a negative. Then I take the square root of both sides. That cancels off this radical here on the left and the root, so I get c is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. And then I stop calling it c, I start calling it d, d for distance. So you've got the distance formula, and that tells me the straight line distance right here between 2 points. I guess we'll call that d now. So I've got a distance formula. I've got my points. Distance formula requires 2 points in x1, y1, and x2, y2. Here's the line equations that we tend to use. There's 3 of them. First of all, there's the standard form of the line, ax plus by equals some constant c. This is called standard form. We almost never solve into this form, but sometimes equations are given to us in this format, particularly in this class. We'll use standard form a lot as our starting point. If I give you the equation instead of asking you to build it from a word problem, you'll probably find me giving it to you in standard form. Then there's 2 other types of line equations. One is this one, y minus y1 equals m x minus x1. M is standing in for slope. Y1 and x1 is a point, so this is called point-slope form. This is best to use if you've got a slope and a point. You have that information, you can cook up the algebraic line equation. If you've got 2 points, x1, y1, x2, y2, that's okay because there's a slope equation. You've got rise, that's that y height difference. That's how much I rise up or down, over run, which is my x difference. So I've got my slope equation. So if I have 2 points, I can calculate m from this equation, and then I just pick one of the points and plug it in for these 2 things. So point slope is best if I already have some coordinates and some slopes, or 2 coordinates, I can cook up the slope. The other one is called slope-intercept. This might be the most famous equation after Pythagorean Theorem, y equals mx plus b. Where I've got a y-intercept, if I plug in 0 for x, this whole part's 0, and I'm just left with b as my y height. This is that point right here, 0 comma b, where this thing here is at height b on my y-axis. M is, of course, my slope. It's called slope-intercept because I have a slope here, and it also gives me the y-intercept. This is the best format to cook up an equation if you want to graph it. So if I have information on the graph with some points and some slopes, and I want to turn it into an algebraic equation, then I use the line point-slope form of the line. If I've got an equation and I want to actually graph it out, then I might use this for my slope-intercept form of the line. So that's some of the initial stuff for section 1.1 and 1.2, coordinates, distances, slopes, and line equations. Let me talk a little bit more about some slopes. Some special slopes. This right here might be the line y equals 2. It's a flat line, it's a horizontal line. And notice something, all the y points on this line are the same height, which means if I plug this into my slope equation, while I'll have different values down here, all my y's are the same value, which means I have 0 divided by some x's, and 0 divided by anything equals 0. So horizontal lines have slope equals 0. On the other hand, I might have something like this. This would be the line x equals 2. This is a vertical line. This slope is going to be undefined. Again, we can see why kind of easily. Here's a couple points. I've got the point 2, 3, and I've got the point 2, 1. If I plug it into my slope equation, my y heights are 3 minus 1. Those are my 2 y points that I've bubbled in here. But my x is always 2, so I get 2 minus 2. This gives me 2 over 0, and this is undefined. DNE is what WebAssign tends to use, does not exist, so you can use that, or alternately, no solution. Either of these are things that are easy to type into those boxes, and they tend to accept that. So for vertical lines, we have an undefined slope. The only other 2 interesting things about slope that I can think to mention is sometimes I've got 2 lines, and they're parallel. So parallel lines have the same slope. line 1 slope will equal line 2 slope. If you've got two equations, you can test out that they have the same slope by solving them into slope-intercept form and then just comparing their slopes. Slightly more interesting ones is perpendicular lines. Perpendicular lines have this. If I give you two lines and you know the two slopes, then generally what we do is that you multiply the two together and that should equal -1. If it does, you know they're perpendicular lines. On the other hand, let's say that I give you a slope and I ask you to find another line that's perpendicular to that. So you're trying to find a second slope. Well, it's going to be -1 divided by m1 because I divide this over to the other side. So this is how you check if you've got two slopes. If you're trying to cook up a line, you use this. Just like up here, I'll use this if I'm trying to cook up a line. If I'm just trying to graph it, I can use slope-intercept. So I've got these two things. And perpendicular lines, usually, if we draw them out, we'll put this little right angle thing here, just to indicate that you're talking about a perpendicular line. Finally, I want to talk about three common equations that we tend to use. Cost, revenue, and profit. We'll see these equations keep on showing up in this course. Cost in this course has two parts. We usually call it a function c of x. There's going to be some number times x. This will be the variable cost. And then it will be plus some constant. This would be what you might call fixed cost. I'm told by students in accounting or economics or other business classes that sometimes these words jiggle around a little bit and mean slightly different things. So if I say something costs $2 per, I don't know, widget, and rent is $3K per month, then my cost of manufacturing widgets is going to be 2x plus 3,000, because x will be my number of widgets that I'm building. I multiply each of those by 2 because that's my material that I put into a widget, and then I've got my rent for my facility. So we generally think of these as variable cost section and this fixed cost section. Next, I've got revenue. Revenue is my income generated. Mostly for us in this class, it's going to be some dollar figure, usually my sale price, times x. So if I sell widgets, I have no idea what a widget is, but they always seem to show up in these economic-y type things. If I sell widgets for $5 per widget, then my revenue equation would be 5x. Lastly, profit is going to equal my revenue, that's my money in, minus cost, my money out. So I would have my revenue being 5x minus my 2x minus 3,000. Notice how the negative distributes over both the terms of my cost equation. That's because secretly this c here is inside a parenthesis and I need to distribute a negative sign through. So my final profit equation is going to be 3x, because for each widget in terms of materials, when I sell it I gain $3, but I have this initial $3,000, that's my monthly rent that I'm dealing with. So this would be my p of x equation. I'll put a little line under all the p's to try to emphasize that it's capital. Generally when I'm talking about c's, I'll try to emphasize capital or lowercase letters. And that's my final piece of advice to you. There is a difference between ax plus bx equals little c versus capital AX plus capital BX equals capital C. In math, y equals mx plus b is not going to be the same as y equals mx plus b. Now obviously for the stand-in letters it doesn't matter, but some people have a bad habit of changing whether their letters are capital or lowercase. And in general in this class I'm going to reserve capital letters to mean some special things. We're going to be talking about some matrices later on. And some other mathematical constructs, sets. So when we're talking about capital letters, I'm going to use those to kind of cue you in, okay, he means this. Also for economics, you don't want to use capital P, you use capital P for profit because lowercase p can be part of your price or your demand function. So we have these traditions, and if you mess with the tradition, that's fine. It's just a tradition, but it can make your life more complicated than it needs to be. So watch out for that upper and lowercase business. It can mess with people more than they think. And some people have been allowed, I think it's kind of bad habits in our K through 12 system, allowed to change their capitals. And it's fine if you start out the right way as long as you're careful, but usually people who are changing the capital letters on me are having trouble, and then I say something ridiculous like, keep all your letters lowercase, and that seems like I'm being unhelpful, but I'm really trying to be helpful. So that's my final comment for Chapter 1.1. There's a couple other 1.1 videos, or Chapter 1 videos out there. This is the one I recommend you watching first. It's the latest. You can watch those other ones if you're having trouble, and of course, always feel free to email me.